Welcome to the Chapter 15.2 lecture on limits and continuity of multivariate functions. Now, I warn you that limits and continuity of multivariate functions is actually much more subtle than the Calculus 1 case. So our definition of the limit of a multivariate function, a function f of xy, is the same definition from Calculus 1, but now generalized to f of xy. So a function f has a limit L as a point xy approaches a fixed point ab, if and only if the difference between that function and the purported limit L can be made arbitrarily small for all p that are sufficiently close to p naught. So here's a picture, and no matter how close we want to make our output to the desired limit, we can choose a little disk around that point p naught, such that for all xy within that disk, then the output is within that desired little radius around the limit. So we define closeness by distance, and more precisely, by making the distance arbitrarily small. That means that for any epsilon greater than 0, no matter how tiny, we can make the output f of xy within epsilon of L by taking the input xy to be within delta of AB for some delta greater than 0. So this diagram illustrates that no matter how close we want to be to the desired limit, no matter how small epsilon is around the desired limit, we can find a delta, which it will itself be arbitrarily small, such that there is some disk around the point p naught, such that for all xy within that disk, then the output of f of xy will be within epsilon of the limit L. Here's a picture of that with the actual function shown. So we have a point A comma B right here. We claim that the limit of f of xy as xy approaches AB is L. And rigorously, that means that for that to be the case, that means that for every epsilon around L, no matter how small, then, so here's an epsilon, and by around L, we mean that we would desire to be within the interval L minus epsilon to L plus epsilon. And we can always be within that interval by choosing a delta such that within the disk of radius delta around the point A comma B, then for all xy within that radius delta, the output of that is within epsilon of L. So imagine it like epsilon is going to 0 and it's squeezing in around L. And no matter how much we squeeze in around L, then we can choose a corresponding little radius around AB, such that for all points in that little radius, then it's within that squeeze. So then the function is squeezed into the limit in this way. Now, this is more subtle than the Calculus 1 definition, because in the Calculus 1 definition, it was an interval, while here it's a whole disk. And the fact that it's a disk means that there are multiple ways of approaching that point AB, in contrast to Calculus 1, where there are only two ways, from the left or from the right. And that means that no matter how we approach the point p naught, at which the function has a purported limit L, then the limit must always be the same along any one of those approaching paths. Because after all, if for every point in here it's within epsilon of L, then that means that, well, along any path, it will also be within epsilon of L. Again, as we squeeze in here, then there will be corresponding smaller and smaller disks here, but the paths continue in those, and that means that along each individual path itself, the limit must be the same. Now, limits for multivariate functions obey the same laws as for a single variate, and importantly, the limit of a multivariate function also obeys these laws. So if you have the constant function, f of xy is always constant, then the limit as xy approaches a b of that constant is the constant. That's reasonably clear. If the function is linear, f of xy is x, then that means that it doesn't care about y is. So as xy approaches ab, it doesn't care what y is, all it cares about what x is. So that means that you get a. And similarly, if f of xy is y, then it doesn't care what x is, and it will approach b, the y coordinate. So these functions are continuous. So another way of looking at it is that the limit is just plugging in the point a comma b. Plugging in ab into x is a, the x part. B isn't plugged into anything. Okay, so limits of multivariate functions. These are all the same things that you learned in Calc 1. They're all still true. Limit of a sum is the sum of the limits. Limit of a difference is the difference of the limits. You can pull out constants from limits. Limit of product is product of the limits. Limit of a quotient is quotient of the limits, provided that the denominator limit exists. If it doesn't exist, then you have 0 over 0 or 1 over 0, etc. And those will either be undefined or indeterminate forms. The limit of a power is the power of the limit, and the limit of a root is the root of the limit. Now, here's a very important strategy for evaluating limits: separation of variables. And this relies on the product rule. So let's find the limit as xy approaches 0, 0 of this guy. Here's the idea. If we can separate this limit into two parts, one of which has only x in it, and the other of which has only y in it, then we can apply the product rule and separate it into two different limits. So in this case, those two different limits are the sine 3y over y part and the e to the x part, e to the 2x part. And now each of these guys is of one variable alone. This is of y alone, and this is of x alone. And that means that they become single variable limits. So at that point, we can just use ordinary calculus 1 limit finding. So this is now just the limit as y approaches 0 of sine 3y over y, and this is the limit as x approaches 0 of e to the 2x. Now, e to the 2x is continuous, and this guy is thus just e to the 2 times 0 is 1. And this guy, this is of the form sine of 0 is 0 over 0. This is of the form 0 over 0. So for this, we need to L'Hopital that. And that L'Hopital, I'll do it up here for space. That's the limit as y approaches 0 of 3 cosine 3y over 1. And that is now continuous, and we can just plug in. That's 3 cosine of 3 times 0 is 3. So this is 3 times 1, and we find that this multivariate limit is 3. Yeah, so if you can separate it into it in this way, always do so, and you're good to go. Let's do another example. Let's find the limit as xy approaches 0, 0 of x over y. So first, can we write this as the limit as xy approaches 0, 0 of x times 1 over y, and then write that as the limit as xy approaches 0, 0 of x times the limit as xy approaches 0, 0 of y, of 1 over y? No. Why not? That is because this limit is undefined, does not exist. So this gets back to what I pointed out here. You can only separate a limit of a quotient with the quotient of the limits if you're not dividing by 0. Otherwise, you have a 0 over 0 or 1 over 0, it's indeterminate or undefined. And you might be looking at this and think, oh, well, it's going to clearly go to 1 over infinity, something like that. Sorry, 1 over 0, something like that, and thus just go to infinity. However, multivariate limits are more subtle. You can approach from many different directions. And for example, if x is always 0, and that would mean that we're approaching along the y-axis. So x is always 0, so we're approaching like this. Then it's always of the form 0 over y. And then it's always 0, no matter how small y is, but not equal to 0. Remember that limits are always around the point, not at the point. So depending upon the direction from which we approach, we will get different answers. So in the direction, in this limit, when x is always equal to 0, then we have that the limit as xy approaches 0, 0 of x over y is the limit as xy approaches 0, 0 of 0 over y is 0. Okay, however, when y is always equal to 0, well, then it's undefined. It's like 1 over 0. And we can also approach from this way. When x is equal to y, then the limit as xy approaches 0, 0 along that direction of x over y is the limit as xy approaches 0, 0 of 1, because these are equal, it's something divided by itself, which is 1. So look at this. We get two different answers depending upon which path we use to approach the limit. So that's what we mean by these different paths here. And for the limit to be defined, we have to get the same answer along every path. Oh, and let me clarify here. This does not imply the limit is undefined by itself. And that is because, yeah, notice I didn't say the limit is undefined. I was saying actually that the thing inside the limit is undefined. A limit, the rigorous definition is that for everything in the domain, then that's what the limit is. But in this case, that means that y equals 0 is not in the domain of the function. And that means that it is meaningless to talk about the limit here. So that it's not in the domain of the function, this implies absolutely nothing about the limit. When we're talking about limits, is always only for things in the domain of the function. So what illustrates that this limit does not exist is not this, it's the fact that these two valid paths, where it's in the domain of the function, yield different answers. Again, for a limit to exist, it has to be the same along all paths. If any two yield different limits, the limit does not exist. Here's another example. Actually, take a moment and think about this. I gave you a hint. Try factoring the numerator and canceling out. You can pause the video if you like. So that numerator factors as x minus y times x plus y, and that's all over x minus y. And these two guys cancel out when x is not equal to y, but x equals y is already not in the domain. And that means that it is always the case. Because again, limits only make sense for values that are in the domain. If something's on the domain, there's no sense in which it can be a valid approaching because it's not in the domain of the function. So this is exactly equal to the limit as xy approaches 4, 4 of x plus y. And at that point, it's nice and continuous, linear in fact. So we can just plug in 4 plus 4 is 8. So that limit does exist. So here's a picture of that. And what this picture points out is that, as we observed, this guy implies that x equals y is not in the domain. But just because it's not in the domain doesn't mean that the limit doesn't exist there. There are lots of functions where there's some point not in the domain where you have a limit. Like here, you can have a limit here from Calc 1, and that's perfectly fine, even though it's not in the domain. It's the same here. The point 4, 4 is not in the domain, because then you have 4 minus 4 is 0, so you're dividing by 0, but it's of the form 0 over 0. So it's not in the domain, but that's perfectly fine. We still have a limit as we approach the point 4, 4, and the point 4, 4 looks, well, somewhere around there. There is 4, 4, not in the domain, but we have a limit as we approach it from all directions, and thus a multivariate limit. Here's an example that I'm not going to go through in detail verbally. You can pause the video and look through it if you like. The point is that, so over here, this guy, we did it by finding the limit along two different paths. And those two paths were x equals y and x equals 0. However, if we just choose two random paths, we might get the same result. And a nice way of choosing all linear paths at the same time is to choose all linear paths at the same time. So we can let y equals mx for some fixed constant m, and we evaluate the limit by substituting y equals mx. So for this guy, we just replace y with mx and see what we get. And if all the m's cancel out and we always get the same thing, then the limit likely exists. But here the m's do not cancel out, and plugging in different m's gets different things. So it's looking at infinitely many paths at once and in a very slick way, and to be able to determine if two different paths yield a different output. And if they do, then we conclude that the limit does not exist. So that's summed up in the two-path test for the non-existence of limits. This is what we did in the x over y example. We found two different paths such that the limits are different along those two paths, and if that's the case, the limit does not exist. Now, we'll be occasionally using this concept, open and closed sets. So first, interior and boundary points. If R is a region, an interior point P lies entirely within R, in the sense that it is possible to find a disk around P such that everything in that disk is contained in R. In contrast, a boundary point Q of R lies on the edge of R in the sense that every disk centered at Q contains at least one point in R and one point not in R. So this diagram might look a bit obscured. Let me redraw this. Here's our point Q. And notice that here's a disk around it. This disk has a point in R and not in R. And for it to be a boundary point, that means that every disk has a point in R and not in R. No matter how small I make this disk around it, you can see that there is some point that's in the white, some point that's in the blue. That's the case for every circle around it. So that means that it lies on the boundary. And you can go ahead and mentally check that for every point inside of R, no matter how close to the boundary, then I can choose a tiny disk around it that's entirely pink. So that would make it an interior point, whereas boundary points don't have that property. And a region is called open if it consists entirely of interior points, and is closed if it contains all of its boundary points. So the difference between open and closed is the following. Well, here's a nice way to illustrate it. Open, x squared plus y squared is less than 1 strictly, is open, while x squared plus y squared is less than or equal to 1 is closed. This disk here contains none of its boundary points. Every point is interior. It's strictly less than 1, while this one here contains its entire boundary. Now, continuity. So this is actually the same definition of continuity from Calc 1, as is the theme. A function f is continuous at a point ab, provided that f is defined at ab, the limit exists, and the limit of f of xy is f of ab. So in other words, you can evaluate the limit by just plugging in the point. We implicitly used this in a previous example. So key takeaway, continuity means that you can evaluate limits by just plugging in the point directly. And continuity composite functions. So if a function u equals g of xy is continuous at ab, and z equals f of u is continuous at the output g of ab, then the composite function f of g of xy is continuous at ab. In other words, you can compose continuous functions and they're still continuous. So first, let's show that this function is continuous. So this is the same function that we dealt with earlier. We have x squared minus y squared over x minus y. The domain of that was whenever x is not equal to y, otherwise you have division by 0. And we found that the limit as we approach 4, 4 was 8 in that previous example. To show that it is continuous at 4, 4, that means that we need to show that the limit as xy approaches 4, 4 of f of x, y is equal to f of 4, 4, but f of 4, 4 is 8, and this part here we already showed in the previous example. So that's all there is to that. Let's find where this function is continuous. 1 over the natural log of xy. So by our knowledge of the natural log and the like, this will be continuous everywhere it is defined. So it's actually the same as finding the domain. The reason it will be continuous everywhere it's defined is that this function has no jumps, gaps, etc. So we need two things. We need that the natural log of xy is not equal to 0, else we have division by 0. Okay, and we need that xy is not equal to 0 or negative, else the natural log is undefined. Okay, well, where is the natural log of xy 0? This means that xy must not be equal to 1, because natural log of 1 is 0. That's the only place it's 0. So that means that y cannot be equal to 1 over x. This guy, xy is not equal to 0. That means that x cannot be equal to 0, and y cannot be equal to 0. And lastly, this guy, that means that, well, xy must be positive. So that means that we are in quadrants 1 or 3. In quadrant 2, x is negative, y is positive. That would mean that the product is negative. And in quadrant 4, x is positive, y is negative. That means that the product is negative. While in quadrant 3, we have a negative times a negative is a positive. So that's why that implies that we're in quadrants 1 or 3. So putting these together, well, that's the domain and where it's continuous. And we see that we cannot have x equal to 1 over y, y equals to 1 over x. So these points are excluded, and we are in quadrants 1 or 3. And also we do not lie on the x or y axes, because x and y, neither of them can be 0. So the points in quadrants 1 and 3 that do not violate that is all of these points. So the white means that we're not in it, and we're not in quadrants 2 or 4. So that is both the domain, and it is where it is continuous. Again, these two are synonymous in this case because natural log and 1 over have no jumps or gaps except where they're already undefined. And that concludes our short section on 15.2. Have a great one.